Imagine all of space and time compressed into a tiny point. A point so minuscule it defies our understanding of size and scale. This point, smaller than an atom, contained everything that would become our vast universe. Every particle, every force, every bit of matter and energy was packed into this infinitesimal space. This is the mind-boggling starting point for the Big Bang theory, a theory that seeks to explain how such a tiny point could give rise to the immense and complex universe we observe today. It's a theory that attempts to explain the origin and evolution of our universe, painting a picture of a cosmos that is dynamic, ever-expanding, and full of wonder. From the initial explosion to the formation of galaxies, stars, and planets, the Big Bang theory provides a framework for understanding the universe's growth and change. The Big Bang theory isn't just an abstract idea, it's supported by a wealth of observational evidence. Scientists have gathered data from various sources, including the cosmic microwave background radiation, which is the afterglow of the Big Bang, and the redshift of distant galaxies, which shows that the universe is still expanding. From the faint afterglow of the Big Bang itself, to the distribution of galaxies across the cosmos, scientists have pieced together a compelling narrative of our universe's history. This narrative helps us understand not only where we come from, but also how the universe has evolved over billions of years. Understanding the Big Bang is about more than just knowing how our universe began. It's about grasping our place in the grand scheme of the cosmos. It challenges us to think about the origins of everything we see around us and our role within this vast expanse. It's about appreciating the incredible journey that matter and energy have taken, from the singularity to the stars and galaxies that grace our night sky. This journey is a testament to the power of natural processes and the beauty of cosmic evolution. As we explore the Big Bang theory, we'll delve into the key stages of this cosmic evolution, examine the evidence that supports it, and confront the mysteries that still linger. Questions about dark matter, dark energy, and the ultimate fate of the universe remain unanswered, driving ongoing research and discovery. Join me as we embark on a journey through time and space to uncover the secrets of the Big Bang. Together, we'll explore the origins of our universe and seek to understand the profound processes that have shaped everything we know. The Big Bang is often misconstrued as a giant explosion from a specific point in space, a cataclysmic event that sent matter flying in all directions. However, this is far from the truth. The reality is much more fascinating and complex. The Big Bang was not an explosion in the conventional sense, but rather a rapid expansion of space itself, a stretching of the very fabric of the cosmos. Picture a balloon with dots drawn on its surface. As you inflate the balloon, the dots don't explode away from each other from a single point on the balloon. Instead, the space between them expands, carrying the dots along with it. This analogy helps us visualize how the Big Bang worked. The dots represent galaxies, and the balloon surface represents space itself. As the balloon inflates, the space between the dots increases, just as the space between galaxies expands. Similarly, the Big Bang involved the expansion of space itself, carrying galaxies and all other cosmic structures along for the ride. This expansion wasn't a violent explosion, but a smooth, continuous stretching of space. This expansion continues to this day, as distant galaxies are observed to be moving away from us at an accelerating rate. The universe is still stretching, and the distances between galaxies are growing larger. The Big Bang theory doesn't posit that our universe exploded into existence within a pre-existing void. Instead, it proposes that space and time themselves came into being at the moment of the Big Bang. Instead, it proposes that space and time themselves came into being at the moment of the Big Bang. This means that the very concepts of space and time were born in that initial moment. This means there was no before the Big Bang, as time itself didn't exist until that initial moment of expansion. The idea of before becomes meaningless when time itself is a product of the Big Bang. This concept can be challenging to wrap our minds around, as we are so accustomed to thinking of time as a constant, ever-flowing entity. We live our lives by the ticking of the clock, but the universe's clock started with the Big Bang. However, the Big Bang theory suggests that time, along with space, has a beginning, marking the birth of our universe as we know it. This moment of creation set the stage for everything that followed. Understanding this fundamental concept of expansion is key to grasping the true nature of the Big Bang. It wasn't an explosion that scattered matter and energy into a pre-existing void. It was the very creation of space and time expanding outward to form the cosmos we observe today. It wasn't an explosion that scattered matter and energy into a pre-existing void. It was the very creation of space and time expanding outward to form the cosmos we observe today. This expansion continues, shaping the universe's future. The Big Bang Theory outlines a universe that has evolved dramatically over billions of years, transitioning through distinct phases marked by extreme changes in temperature, density, and the fundamental forces governing the cosmos. This theory, which is the cornerstone of modern cosmology, provides a comprehensive explanation for the origin and evolution of the universe, from its earliest moments to the present day. The earliest period, known as the Planck epoch, remains shrouded in mystery. This epoch, lasting only a fraction of a second, is characterized by conditions so extreme that our current understanding of physics breaks down. Scientists continue to explore this enigmatic phase, hoping to unlock the secrets of the universe's birth. From this point of unimaginable density and temperature, the universe expanded and cooled, transitioning into the inflationary epoch. This rapid expansion, occurring in less than a trillionth of a second, stretched the fabric of space-time itself, smoothing out any initial irregularities and setting the stage for the universe's large-scale structure. During this incredibly brief period, the universe underwent exponential expansion, stretching out any initial irregularities and setting the stage for the large-scale structure we observe today. This inflationary period is crucial for explaining the uniformity of the cosmic microwave background radiation, a relic of the early universe that provides a snapshot of its infancy. As the universe continued to cool, the fundamental forces of nature began to separate, and the first elementary particles, such as quarks and leptons, began to condense out of the primordial energy bath. This separation of forces, known as symmetry breaking, is a key event in the universe's evolution, leading to the distinct forces we observe today: gravity, electromagnetism, and the strong and weak nuclear forces. This period marked the transition from a universe dominated by energy to one where matter began to play a significant role. Quarks combined to form protons and neutrons, the building blocks of atomic nuclei, while leptons, such as electrons, remained free to interact with these nuclei. The formation of protons and neutrons followed, paving the way for the next crucial stage, the creation of the first atoms. These subatomic particles combined to form the nuclei of hydrogen and helium, the simplest and most abundant elements in the universe. Around 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and neutrons, forming the first atoms of hydrogen and helium. This process, known as recombination, allowed the universe to transition from an opaque, plasma-filled state to a transparent one, where light could travel freely. This event, known as recombination, marked a significant turning point. The universe, once opaque to light, became transparent, allowing photons to travel freely for the first time. This transparency is captured in the cosmic microwave background radiation, a faint glow that permeates the universe and provides a window into its early history. Over vast stretches of time, these initial clouds of hydrogen and helium, under the influence of gravity, coalesced to form the first stars and galaxies. These early stars, known as population 3 stars, were massive and short-lived, playing a crucial role in enriching the universe with heavier elements through their explosive deaths. Inside the fiery cores of these early stars, heavier elements were forged through nuclear fusion, seeding the universe with the building blocks of planets and ultimately life itself. The death of these stars and supernova explosions scattered these elements across the cosmos, contributing to the formation of new stars, planets, and eventually, the complex structures we see today. The Big Bang Theory thus paints a picture of a universe that has undergone a remarkable transformation from an incredibly hot, dense state to the vast, complex cosmos we observe today. This ongoing evolution continues to shape the universe, driving the formation of new stars, galaxies, and other cosmic structures. Each stage in this evolution has left its imprint on the universe, providing scientists with clues to piece together the story of our cosmic origins. By studying the cosmic microwave background radiation, the distribution of galaxies, and other astronomical phenomena, researchers continue to unravel the mysteries of the universe, deepening our understanding of its past, present, and future.